The early universe was almost perfectly smooth. No swirls, no whirlpools, nothing spinning at all, just a faint, even glow stretched across everything. And yet look around today. Planets turn, stars spin, galaxies wheel through the dark. Collapsed stars whirl hundreds of times every second. Somehow, out of near-perfect stillness, the cosmos learned to rotate almost everywhere we look. Nobody wound it up. No cosmic hand set it turning. So where did all this motion come from? Why does contracting matter speed up? And why do some objects spin fast enough to tear themselves apart while others barely move at all? The answer isn't a mysterious force. It's something far stranger, hiding inside the rules themselves. Tonight we follow that motion back to its source and change how you see the whole sky. Before we go any further, if you enjoy slow, careful journeys through how the universe actually works, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Think back to the beginning of everything. Not the fiery, chaotic explosion you might picture, but something almost the opposite of chaos. In the first few 100,000 years after the Big Bang, the universe was astonishingly, almost unbelievably smooth. If you could have stood inside it and looked around, you would have seen a nearly uniform glow in every direction. A sea of hot gas spread out so evenly that the differences from one place to another were tiny beyond imagining. We can actually measure this today. We look at the oldest light in existence, the faint afterglow left over from that early era, and what we find is a smoothness of about 1 part in 100,000. That means if you compared one patch of the early universe to another, they match to within 100,000th of each other. It was, for all practical purposes, featureless, still, calm, almost perfectly balanced. And yet, look at the universe now. Almost nothing is still. The earth beneath your feet is turning, carrying you around its axis once a day. The earth is also racing around the sun. The sun itself is wheeling around the center of our galaxy, dragging the entire solar system along a slow, enormous circle that takes hundreds of millions of years to complete. Galaxies rotate. Vast disks of gas swirl around newborn stars. Collapsed dead stars spin so fast they complete hundreds of full turns every single second. Everywhere you point a telescope, you find motion, circulation, rotation, orbiting. The universe that began in near-perfect stillness has somehow filled itself with spin. So here is the puzzle we're going to work through tonight, slowly and carefully. How does a smooth, calm, nearly motionless universe become one where rotation shows up almost everywhere you look? Nobody reached in and set it spinning. There is no giant cosmic hand cranking a handle. There is no mysterious universal force whose only job is to make things turn. So where does all this motion actually come from? And why does it seem to organize itself, again and again, into the same shapes? Disks, orbits, whirlpools, spinning cores. The answer, and I want to be honest with you right from the start, is not a single dramatic secret. It's something quieter and, in a way, more beautiful. Rotation appears throughout the universe because of a handful of simple rules working together over and over at every scale. Tiny imperfections that could never be fully avoided. Gravity, which relentlessly pulls matter together. And a conservation law so strict that once a little bit of turning motion exists, it cannot simply be thrown away. Put those together, and rotation isn't strange at all. Rotation becomes almost inevitable. But before we can follow that story, we need to be careful about our words. Because there are several different things people lump together when they say something is spinning, and they are not the same thing. Getting them straight is the key that unlocks everything else. Let's start with rotation. Rotation is when an object turns around an axis that runs through itself. The Earth rotating is a perfect example. There's an invisible line running through the North and South poles, and the Earth turns around that line once roughly every 24 hours. A spinning top rotates. A merry-go-round rotates. The defining feature is that the object turns about a line passing through its own body. The object stays in one place, more or less, and simply revolves upon itself. Now compare that to revolution or orbital motion. This is when one object travels around another. The Earth revolving around the Sun is orbital motion. The Earth is not turning on an internal axis in this case. It is traveling a great loop around a point far outside itself, around the Sun, which sits about 93 million miles away. The Moon orbiting the Earth is orbital motion. A planet circling its star is orbital motion. The key difference is the location of the center. In rotation, the center is inside the object. In orbital motion, the center is somewhere outside it. These two often happen at the same time, which is exactly why people confuse them. The Earth rotates on its axis once a day, and it also revolves around the Sun once a year. Both are true simultaneously. One is spinning in place, the other is traveling in a loop. When you hear someone say a planet is spinning, you have to ask which one they mean, because these are genuinely different motions with different causes and different consequences. And then there's the deeper idea underneath both of them, the concept that ties the whole night together: angular momentum. This is the one to hold on to. Angular momentum is, roughly speaking, a measure of how much rotational motion something has. But it's more subtle than just how fast a thing is turning. Angular momentum depends on three things: how much mass an object has, how fast it's moving around a center, and crucially, how far that mass is from the center. That last part, the distance from the center, turns out to matter enormously. It's the hidden ingredient that makes the whole story work. Here's why angular momentum deserves its own special place in our thinking. Ordinary momentum, the kind you have when you're walking in a straight line, describes motion from one point to another. Angular momentum describes motion around a point, and nature has a rule about it, one of the deepest and most reliable rules we know. In an isolated system, one where nothing outside is pushing or twisting it, the total angular momentum cannot change. It is conserved. It can be moved around, shared between objects, concentrated or spread out, but the total amount stays fixed. You cannot create it from nothing, and you cannot make it vanish into nothing. Now hold that rule in your mind, because it leads to something surprising. And this is the first idea I really want you to absorb tonight. An object does not need to start out obviously, dramatically spinning in order to end up with a huge amount of rotation later. That sounds almost contradictory at first. If something is barely turning now, how can it be whirling later without some new force spinning it up? But remember what angular momentum depends on. It depends not just on how fast something moves around a center, but on how far the mass sits from that center. This means you can have a large, slow, lazily drifting cloud that is barely turning at all. So slowly you might not even notice. And yet, because it is enormous, because its material is spread across an unimaginably wide region, it can be carrying an enormous store of angular momentum. That angular momentum is real. It's there, banked away, hidden inside a motion so gentle it looks like nothing. And then something happens. The cloud begins to shrink, Gravity pulls it inward. All that spread out material starts falling toward the middle, and the distance from the center gets smaller and smaller. But the angular momentum, that conserved total, cannot disappear. So as the distance shrinks, something else must grow to compensate. The speed of the turning has to increase. The cloud that was drifting so slowly you'd swear it was standing still spins up faster and faster as it collapses. The rotation was there all along, waiting, disguised as near stillness because it was spread across such a vast space. Contraction is what reveals it. We'll unpack the exact mechanism of that speeding up in a moment, because it's the heart of everything. But first, I want to deal with an objection you might reasonably be forming right now. You might be thinking, fine, but what if the cloud isn't turning at all? What if it truly has zero rotation? Then there's no angular momentum to reveal, no matter how much it shrinks. And that's correct. If a cloud genuinely had exactly zero angular momentum, collapsing it would not produce spin. It would just fall straight inward, every particle diving directly toward the center, and pile up into a single point without ever circulating. So why doesn't that happen? Why doesn't matter simply collapse straight in, cleanly and radially, everywhere in the universe? Why do we get disks and whirlpools instead of neat, motionless heaps? The answer is that perfectly straight-in collapse, what physicists call perfectly radial, perfectly symmetrical collapse, is very nearly impossible in the real universe. Not just unlikely, almost unimaginably unlikely. And understanding why is one of the most satisfying insights in all of physics. Picture what perfectly radial collapse would actually require. Every single particle in the cloud would have to be moving exactly toward the geometric center. Not a little to the left, not a little to the right, not with the slightest sideways drift. Dead on, straight at the middle, every one of them with no exceptions. Furthermore, the cloud itself would have to be perfectly symmetric, exactly the same density in every direction, so that gravity pulled equally from all sides and never nudged anything off course. There could be no lumps, no thicker patches, no thinner patches, nothing to break the perfect balance. Think about how delicate that is. It's like trying to balance a needle perfectly upright on its point. In principle, there's an exact position where the needle would stand balanced forever, with gravity pulling straight down through the tip. But in practice, the tiniest breath of air, the faintest vibration, the smallest imperfection in the needle itself, and it topples. The balanced state exists mathematically, but it is so fragile, so exquisitely sensitive to the smallest disturbance, that you will never actually find a needle standing that way in the real world. Perfectly radial collapse is the cosmic version of that balanced needle. It's a knife-edge condition that any real disturbance destroys. And the real universe is absolutely full of disturbances. Remember that early smoothness I mentioned? The 1 part in 100,000? That number cuts both ways. Yes, the early universe was astonishingly smooth, but it was not perfectly smooth. There were tiny variations, tiny regions that were a hair denser than average and others a hair thinner. Those variations were the seeds of all structure, and they mean that when a cloud of gas begins to collapse under gravity, it is never collapsing from a perfectly uniform starting point. One side is always a little denser than another. One region always pulls a little harder. And the moment gravity is even slightly stronger on one side than the other, matter doesn't fall straight towards the center. It falls at an angle. It gets nudged sideways. This is the crucial thing. Those tiny sideways motions, those little off-center drifts, are exactly what carry angular momentum. A particle heading straight for the center has no angular momentum about that center. But a particle that misses the center even slightly, that swings past it a little to one side, is moving around the center, not merely toward it. And motion around a center is angular momentum. So the very imperfections that make perfectly radial collapse impossible are the same imperfections that guarantee the collapsing cloud is carrying at least a little bit of rotation. Let me make this concrete with something you can picture. Imagine water draining out of a bathtub or a sink. In principle, if the water were perfectly still and the drain were perfectly centered, and everything were perfectly symmetric, the water would just sink straight down, no swirl at all. But that essentially never happens. In the real world, the water always has some tiny leftover motion, a faint drift from when you filled the tub, a slight asymmetry in the basin, a little current here or there, and as the water is pulled toward the drain, toward a smaller and smaller region, that faint drift gets concentrated and amplified until you see it clearly. A swirling whirlpool, spiraling down. The whirlpool wasn't put there on purpose. It emerged because the water had a little bit of sideways motion to begin with, and squeezing it toward the drain revealed that motion as an obvious spin. The universe builds its whirlpools the same way, just on a scale beyond comprehension. Now we're ready to look closely at the engine that drives all of this, the reason contracting matter speeds up. This is conservation of angular momentum in action, and there's a familiar demonstration almost everyone has seen, so let me use it briefly, and then we'll launch straight from it into the cosmos. Picture a figure skater spinning on the ice. She starts her spin with her arms stretched out wide, turning at a moderate pace. Then she pulls her arms in tight against her body, and without pushing off the ice, without any new effort to spin faster, she suddenly whirls much more rapidly. You've seen it. It looks almost like magic, but it's simply conservation of angular momentum. With her arms out, her mass is spread far from her axis, so she can turn slowly and still have a certain amount of angular momentum. When she pulls her arms in, she brings that mass close to the axis. The distance shrinks, and because her total angular momentum has to stay the same, her spin rate has to climb to make up for it. Less distance means more speed. She didn't add rotation. She just concentrated the rotation she already had into a smaller radius, and the speed shot up in response. That's the skater, and that's the last time we'll lean on her, because now I want you to see that this exact same principle is what's happening when a cloud in space collapses. Only there, the arms pulling in aren't a person's arms. They are the entire outer reaches of a gas cloud, falling inward under gravity across distances measured in trillions upon trillions of miles. Consider an enormous cloud of gas and dust drifting in space, the kind of cloud that eventually forms stars. It might stretch across dozens of light years. It is turning ever so slightly. Maybe it completes one full rotation over millions of years, a motion so slow it's almost meaningless to call it turning at all. But that gentle turn is the skater's outstretched arms. The cloud's mass is spread across a colossal radius, so even a whisper of rotation adds up to a genuine store of angular momentum. Then gravity takes over. The cloud begins to collapse, its material streaming toward the center, and just like the skater pulling her arms in, the collapsing cloud is bringing its mass closer and closer to the axis. The radius shrinks by factors of thousands, then millions. And conservation of angular momentum demands its price. As the radius shrinks, the rotation speed must climb, and climb and climb. That cloud that took millions of years to turn once can wind up spinning with tremendous speed, simply because its material has fallen so far inward. Nothing spun it up from outside. It reeled in its own arms, and the leftover motion it had all along came roaring to the surface. This is why contracting matter almost always rotates faster as it shrinks. It's not a special property of gas clouds or of space. It's a direct, unavoidable consequence of the conservation law, combined with the facts that gravity pulls things inward. Anytime you take a rotating system and make it smaller, the rotation intensifies. Grow it, and the rotation slows. Squeeze it, and it whirls. The universe is constantly squeezing matter with gravity, and so the universe is constantly making things spin faster. Let me pause here and address something important, because I don't want to overstate the case, and honesty matters more than a tidy story. This does not mean the rotation speeds up without limit, or that it can never slow down, or that every object must spin forever at the same rate. It just means that during contraction, with angular momentum conserved and nothing carrying it away, the spin increases. Later in our journey, we'll see all the ways the universe can bleed rotation off an object and hand it somewhere else, so that a spinning thing slows over time. Angular momentum being conserved doesn't mean it's frozen in place. It means the total is preserved, even as it moves around. Keep that distinction in your pocket. It will matter enormously later. There's another subtlety worth pinning down now. The amount a cloud speeds up depends on how much its radius shrinks, and the relationship is dramatic. Because angular momentum depends on the radius squared. When the radius shrinks, the rotation rate has to rise by the square of that shrinkage to keep the total fixed, which means the effect is not gentle. If a rotating cloud collapses to 1/10 of its original size, it doesn't spin 10 times faster. It spins roughly 100 times faster. Collapse to 100 the size, and the spin can climb by a factor of about 10,000. This is why a barely detectable initial rotation, something so slow you would swear the cloud was motionless, can turn into a furious spin by the time collapse is finished. The shrinking of the radius acts like a lever, and it's an extraordinarily powerful one. A hint of rotation at large scale becomes a dominant, defining feature at small scale. And this immediately explains why gravity and rotation are locked in a kind of permanent tension throughout the cosmos. Gravity wants to pull everything straight inward, to collapse a cloud down toward a single point. But as the cloud shrinks, its rotation speeds up, and rotation resists being pulled inward. The faster something circles the center, the harder it is to force it all the way in, because the circling motion tends to fling material outward, opposing the inward pull. So you get a competition. Gravity pulls in, rotation pushes back against that inward collapse, at least in certain directions. And out of that competition comes structure. The matter can't all fall to the center because the more it falls, the faster it spins, and the harder it resists falling further. Something has to give, and what gives, as we'll see, is the shape of the whole system. Here's a way to feel the logic of it. Imagine you're swinging a ball on a string around your head. As long as you keep swinging, the ball circles you and the string stays taut. And no matter how hard the string pulls the ball toward your hand, the ball keeps circling rather than crashing into your fingers. Its circular motion holds it out at a distance. Now, that's a rough picture, but it captures something true. An object with enough motion around a center resists being pulled all the way to that center. Rotation defends a certain distance, and in a collapsing cloud, that defended distance is what stops all the matter from simply falling into the middle. Along the direction of the spin, matter is held back, but there's a direction where rotation offers no defense at all, and that's where things get interesting, though that's a story for a little further on. Let me tie together where we've arrived, because we've built something important and I want it solid before we go anywhere else. We started with a universe that began smooth and calm, and we asked how it filled itself with rotation. And piece by piece, an answer has emerged that requires no mysterious force at all. First, we learned that rotation, orbital motion, and angular momentum are related but genuinely different things, and that angular momentum, the deep conserved quantity, depends not only on how fast something turns, but on how far its mass sits from the center. Second, we saw that because of that dependence on distance, an object doesn't need to begin with obvious rapid spin. A vast, slowly drifting cloud can secretly hold a great store of angular momentum, hidden in a motion so gentle it looks like stillness. Third, we understood why matter almost never collapses in a perfectly straight-in, symmetric way. Perfectly radial collapse is a knife-edge condition, as fragile as a needle balanced on its point, and the real universe is riddled with the tiny density variations and sideways motions that knock any collapse off that perfect balance. Fourth, those very imperfections, those little off-center drifts, are precisely what carry angular momentum, guaranteeing that a collapsing cloud is always turning at least a little. And fifth, we saw that conservation of angular momentum, the same rule that makes a skater speed up when she pulls in her arms, forces any contracting cloud to spin faster as it shrinks, with a leverage so powerful that a whisper of initial rotation becomes a roar. That is the seed of nearly everything we'll explore. It is a machine with a small number of moving parts: imperfection, gravity, and conservation. And here is what makes it so powerful as an explanation. It doesn't apply to just one kind of object or one scale of the universe. It applies to anything that collapses under gravity while carrying even a trace of rotation, which is essentially everything. A cloud that will become a single star. A larger cloud that will become a whole cluster of stars. The disk of material that will condense into planets. The core of a dying star crushing down into something impossibly dense. The gigantic clouds that will become entire galaxies. In every one of these cases, the same three ingredients are present. There's always some tiny asymmetry, gravity is always pulling inward, and angular momentum is always conserved. So in every one of these cases, rotation tends to emerge, organize, and intensify. This is why rotation is so common in the universe, and it's a much more satisfying answer than imagining some cosmic engine winding everything up. Rotation is common because its absence would require perfection, and the universe does not do perfection. Exact symmetry is vanishingly rare. Perfectly straight-in collapse essentially never happens. And once even a sliver of rotation is present, the conservation law amplifies it every time gravity shrinks the system. Motion around a center is not the exception that needs explaining. Motion straight toward a center, with no swirl at all, is the exception. And it's an exception so delicate that nature almost never achieves it. I want to leave you, before we move on, with one more thought to sit with, because it reframes the whole question you might have started with. You might have begun tonight wondering why so much of the universe spins, but now you can see that the better question, The more honest question is why the universe would ever expect things to stand still. Stillness, in a universe governed by gravity and shot through with tiny imperfections, is the fragile and unnatural state. The moment matter starts to gather and fall together, the faintest breath of leftover motion gets caught up, concentrated, and revealed. The universe didn't have to be wound up. It only had to be imperfect and obey a single conservation law, and rotation followed as surely as water finding the drain. Everything from here forward is that same seed, planted in different soil. When we watch a spinning disk of gas form around a newborn star, when we see the planets of a system all orbiting in the same direction, on nearly the same plane, when we encounter collapsed stellar core spinning hundreds of times a second, when we look at the slow, majestic wheel of a galaxy, we will be looking at this one simple story told again and again at wildly different scales. A tiny asymmetry, gravity pulling in, angular momentum conserved, faster, more organized rotation emerging from what began as near-perfect calm. Hold that chain in your mind, and the spinning universe stops being a mystery and starts being something you can genuinely understand. So let's follow the seed as it grows. Let's watch what happens when one of these vast, slowly turning clouds actually begins to collapse in earnest, and see how it builds, out of drifting gas and a whisper of rotation, an entire family of worlds. Let's follow that seed now, out into a real corner of a real galaxy, and watch it grow into worlds. Picture one of those enormous clouds we've been talking about, a great sprawling bank of gas and dust drifting in the dark between the stars. Astronomers call these molecular clouds, and they are staggeringly large, sometimes spanning tens or even hundreds of light years, holding enough material to build thousands of stars. They are cold, they are dim, and they are mostly hydrogen, laced with their little helium and a fine haze of dust, the microscopic grains of rock and ice and soot that will one day become the ground beneath somebody's feet. And crucially for our story, these clouds are never perfectly still, and they are never perfectly smooth. Where does their motion come from? This matters because we said in the beginning that angular momentum can't appear out of nowhere. So a cloud that will one day spin must have inherited its motion from somewhere. And it did. From many places at once. These clouds are stirred constantly by the turbulence of the galaxy around them. Gas in a galaxy is always churning, buffeted by the shock waves of exploding stars, squeezed by the passage of spiral arms, pushed and pulled by the gravity of everything nearby. A giant molecular cloud sits in the middle of all this churning, like a raft on a restless sea. It gets tugged on one side by a neighboring clump of gas, nudged on another by a passing star, rippled through by the pressure wave of a distant supernova. None of these influences is trying to make the cloud rotate, but the combined effect is that different parts of the cloud end up drifting in slightly different directions. And anytime one region of a cloud drifts one way, while another region drifts a little differently, the cloud as a whole ends up with a net twist. A faint, slow, almost imperceptible rotation. The skater's outstretched arms, once again, but now the arms are light years long. So here is our cloud. Vast, cold, faintly turning, and lumpy. It has denser knots and thinner voids scattered throughout, because turbulence never leaves anything smooth. And within one of those denser knots, gravity begins to win. The knot has enough material packed closely enough that its own gravity starts pulling it inward faster than the surrounding pressure can push back. The collapse begins. Now, watch what happens, because it's the story we just built playing out in the real world. As this knot of gas falls inward, its radius shrinks dramatically. A region that might have started light years across begins collapsing down towards something the size of a solar system, and eventually towards something the size of a star. That's a reduction in size by a factor of millions. And we know exactly what conservation of angular momentum does when a rotating thing shrinks by a factor of millions. It speeds up, and it speeds up with that ferocious leverage we described, where the rotation climbs with a square of how much the radius drops. The whisper of a turn the cloud inherited from galactic turbulence becomes, as the material falls inward, a genuine and unmistakable spin. And here we arrive at one of the most beautiful and important consequences in all of astrophysics, the thing that shapes the entire character of planetary systems. The collapsing gas does not, and cannot, simply fall all the way into the center to make a star and nothing else. If it could, the young star would swallow everything, and there would be no planets, no moons, no leftover material at all. But rotation forbids it. Let me show you exactly why. Think about the cloud as it collapses and spins faster. Consider a bit of gas somewhere out in the cloud, circling the center. Gravity is pulling it inward, toward the middle. But because it's circling, it has that rotational motion that resists being pulled all the way in, exactly like the ball on the string defending its distance. Now here's the key insight. This resistance only works in certain directions. Consider the plane that the rotation happens in, the flat disc-shaped region the material is circling around, like the plane of a spinning record. Within that plane, matter trying to fall inward is opposed by its circular motion. It can't easily reach the center. Its own orbiting holds it out at a distance. But now think about the direction along the axis of rotation, straight up and down relative to that spinning plane, like the spindle sticking up through the center of the record. In that direction, the rotation offers no resistance at all. A bit of gas sitting above the plane, trying to fall down toward the center, isn't circling around that up-down direction, so nothing holds it back. It just falls. Gravity pulls it straight down toward the central plane with nothing to oppose it. Do you see what this means? Matter can fall freely along the axis, collapsing down toward the central plane. But matter cannot easily fall inward within the plane, because rotation defends it there. So the cloud collapses much more in one direction than the others. It falls in from top and bottom, flattening, while the rotation holds it spread out sideways. A great puffy ball of gas, collapsing under gravity but spinning as it does, is squashed by its own physics into a flattened, spinning disk. The top and bottom cave in, the sides hold their ground, and what you're left with is a broad, rotating pancake of material with a young star forming at its dense, hot center, surrounded by a swirling disk of gas and dust that couldn't fall all the way in. This flattened, spinning structure has a name. We call it a protoplanetary disk, which simply means a disk from which planets are about to form. And it is not a rare or exotic thing. When astronomers point their most powerful telescopes at regions where stars are actively being born, they see these disks everywhere, glowing rings and spirals of material encircling infant stars. The disk is the natural, expected, almost unavoidable result of collapsing a rotating cloud. Spin plus gravity plus conservation gives you a disk, essentially every time. Now, I don't want to leave the impression that the disk is a permanent traffic jam, with material simply stuck out there forever, unable to reach the star. Some of it does eventually reach the star, and understanding how connects directly to our deeper theme. The problem the infalling gas faces is precisely its angular momentum. To fall onto the star, a parcel of gas has to get rid of the rotation that's holding it out at a distance. It can't destroy that angular momentum because the conservation law won't allow it, but it can hand it off. Within the crowded, swirling disk, neighboring rings of material rub against each other. The inner parts of the disk orbit faster than the outer parts, so there's a constant friction, a churning and dragging between adjacent regions. And through that friction, inner material passes some of its angular momentum outward to material farther out. Having shed its rotation to its neighbors, the inner gas can finally spiral down and join the star. Meanwhile, the outer material, having received that angular momentum, drifts even farther out. So the disk sorts itself. Some matter loses its spin and falls in to feed the star, while other matter gains that spin and moves outward. Angular momentum wasn't eliminated. It was redistributed, shuffled from the material that fell into the material that stayed out. Like, hold on to that idea of redistribution. It is going to come back again and again. So we have our young star at the center, and around it a vast rotating disk of gas and dust, all of it circling the same way, because it all came from the same collapsing, spinning cloud. And now the planets begin to build. Within that disk, the dust grains, those tiny specks of rock and ice, begin to collide and stick together. First they form clumps, then pebbles, then boulders, then bodies miles across, and eventually worlds. This building up takes a long time and involves a lot of violence, but the essential point for our story is where it happens and how it moves. The planets are assembling out of the material of the disk, and the disk, remember, is a single flattened sheet, all rotating in the same direction around the star. So the planets inherit that arrangement, they form within the plane of the disk, and they orbit in the direction the disk was already turning. This is the answer to a question you may have wondered about when you first saw a diagram of the solar system. Why do all the planets orbit the sun in roughly the same direction, and roughly in the same flat plane? Why isn't the solar system a chaotic jumble of orbits, pointing every which way? Some planets going clockwise, some counterclockwise, some looping over the poles? The answer is now clear. The planets don't orbit in the same plane and direction by coincidence or by design. They orbit that way because they all condensed out of the same spinning disk. And that disk had a single direction of rotation, inherited all the way back from the faint turn of the original cloud. The flatness of a planetary system is a fossil, a preserved record of the rotating disk it came from. When you look at the orderly coplanar orbits of the planets, you're looking at the ghost of the protoplanetary disk that built them, and behind that, the ghost of a slowly turning cloud in the dark. And this isn't just a story about our own solar system. As astronomers have discovered thousands of planets orbiting other stars, they found the same pattern over and over. Planetary systems tend to be flattened. The planets tend to share a common plane and a common direction. There are exceptions and complications, which we'll get to, but the broad rule holds across the galaxy. Planets form in disks, and disks are flat and rotating, so planetary systems are flat and rotating too. The same seed, planted around countless different stars, grows the same basic shape. But now I want to draw a careful distinction, because this is exactly the kind of place where it's easy to blur two different things together and we promise to keep them separate. We've been talking about the orbital motion of the planets, the way they revolve around the star, all in the same direction and plane. That orderliness comes straight from the disk. But the way an individual planet rotates, the way it spins on its own axis, is a separate matter, and it does not have to follow the same tidy rule at all. Here's why. A planet's orbit is set by the large-scale motion of the whole disk it formed from, a motion shared by an enormous amount of material all going the same way. That's a robust, stable inheritance. It would take something dramatic to reverse a planet's orbit. But a planet's spin on its own axis is a much more delicate thing, set by the details of how that particular planet came together, and it's vulnerable to being knocked around. During the chaotic era of planet building, worlds grew by absorbing countless smaller bodies, and each of those impacts delivered a little twist, some adding to the spin, some subtracting from it, some tilting the axis one way or another. The final spin a planet ends up with is the sum of all those collisions, and that sum can come out pointing in almost any direction, at almost any speed. Our own solar system shows this beautifully. Most of the planets do spin in the same general direction they orbit, a leftover of the disk's rotation carried down into their individual spins. But not all of them, and not neatly. Venus rotates backward compared to the others, turning slowly in the opposite direction, so slowly that a single day on Venus lasts longer than its entire year. Uranus is stranger still. It's tipped over almost completely onto its side, its axis lying nearly flat in the plane of its orbit, rolling around the sun like a ball rather than spinning like a top. The most likely explanation for these oddities is exactly what we'd expect from the collision story. Somewhere in their violent youth, these worlds were struck by enormous impacts, blows powerful enough to knock their spins clean off the pattern the disk had set. The orbital motion, protected by the momentum of the whole system, stayed orderly. The individual spin, fragile and easily overturned, did not. And impacts aren't the only thing that shapes a planet's rotation over its long life. A planet's spin can change through its own internal evolution, as material shifts around inside it and its shape settles. More importantly, spin can be altered by tidal interactions, and tides are one of the great redistributors of angular momentum in the universe, so it's worth understanding them properly. You already know tides as the rising and falling of the sea, and you may know they're caused by the moon. But the deeper story of tides is a story about angular momentum being passed from one body to another, and it plays out across the whole solar system. Here's the essence of it. When one body orbits close to another, the gravity of each pulls unevenly on the other, tugging harder on the near side than the far side. This stretches each body slightly, raising bulges. Now, if the bodies are also rotating, those bulges get dragged out of perfect alignment, and the misalignment creates a gentle, persistent gravitational pull between the two that acts like a brake on one and a push on the other. Through this mechanism, one body can slowly transfer its rotational angular momentum to the other's orbital motion, or slow its own spin, over millions and billions of years. Our own moon is the clearest example, and it demonstrates two effects at once. First, the Earth's tidal pull on the moon long ago slowed the moon's rotation until it settled into a locked state, always keeping the same face toward us. That's why we only ever see one side of the moon. Its spin has been tidally braked into step with its orbit. Second, The moon's tidal pull on the Earth is slowly stealing a little of Earth's rotational angular momentum and handing it to the moon's orbit. The effect is tiny, but it's real and measurable. Earth's day is very gradually lengthening, and the moon is very gradually drifting farther away, spiraling outward as it receives the angular momentum Earth is giving up. Notice what's happening here in terms of our grand theme. The total angular momentum of the Earth and Moon system stays the same, but it's being moved, transferred out of Earth's spin and into the Moon's orbit. The Earth spins a hair slower each century. The Moon climbs a little higher. Nothing is created, nothing destroyed. It's all redistribution. The same lesson the protoplanetary disk taught us, now written across the sky in the rising and falling of the tides. This redistribution goes on all over the solar system, wherever moons and planets and rings interact. And rings are a wonderful illustration, because a planet's ring system is essentially a miniature version of the protoplanetary disk we started with, obeying the very same physics. A ring is a broad, flat, rotating sheet of countless small particles, all orbiting a planet in the same direction and plane, held into a disk for exactly the reasons we discussed. Rotation defends the sideways spread, while gravity flattens the top and bottom. Within a ring system, angular momentum gets shuffled around constantly. Moons embedded in or near the rings tug on the ring particles. The particles tug back. Material gets herded into sharp edges and gaps and waves. Some of the beautiful structure we see in a planet's rings, the crisp divisions and delicate ripples, is the visible signature of angular momentum being traded back and forth between moons and ring particles. A ring is a living demonstration of disk physics, close enough to study in detail, playing out the same drama that once built the planets themselves. Whole systems of moons participate in this too. Many planets are circled by families of moons, and these moons often fall into elegant relationships where their orbits are linked. One moon completing a certain number of orbits in exactly the time another completes a different number. These arrangements, called resonances, arise because the moons exchange angular momentum through their repeated gravitational tugs, gradually nudging one another until they settle into these locked, rhythmic patterns. A system of moons is not a random scattering. It's a network through which angular momentum flows and settles, finding stable configurations over long stretches of time. And the moons themselves, of course, mostly orbit in the same direction and plane as the planet's rotation and its ring, because many of them formed from a disk of material around the young planet, a smaller echo of the disk that formed the planets around the star. Disks within disks, the same shape repeating at every scale, all of it descended from that first faint turn. Not every moon follows the pattern, and the exceptions tell their own story, consistent with everything we've built. Some moons orbit their planet backward against the direction of the planet's spin, or on steeply tilted paths that don't match the orderly plane of the others. When we find a moon like that, we can be fairly confident it didn't form from the planet's own disk. Instead, it was probably a wanderer, a small body drifting through space that strayed too close to the planet and was captured by its gravity. A captured moon carries whatever motion it happened to have when it was caught, which need not match the planet's rotation at all. So a backward or tilted moon is a clue to its origin, a sign that it joined the family from outside rather than being born into it. Once again, the orderly cases and the disorderly cases both make sense through the same lens. Material that shares a common disk shares a common rotation. while material that arrives from elsewhere brings its own independent motion. Let me gather all of this together because we've travelled a long way from that cold, drifting cloud, and I want the whole arc to stand clearly in your mind. We began with a vast molecular cloud, faintly turning because galactic turbulence and the tugs of its neighbours had left it with a whisper of net rotation. Gravity found a dense knot within it and pulled that knot inward. As the knot collapsed, shrinking by a factor of millions, conservation of angular momentum spun it up, exactly as it spun up the skater and the whirlpool, but now with the ferocious leverage of an astronomical collapse. The rotation, harmless along the axis but defended in the plane, forced the collapsing gas to flatten into a spinning disk rather than falling straight into the center. A star lit up at the dense middle, and around it lay a broad, rotating pancake of leftover material, the protoplanetary disk. Friction within that disk let some material shed its angular momentum to its neighbors and fall onto the star, while the rest, having gained that angular momentum, spread outward. Out of the disk, dust gathered into worlds, and because they formed from a single spinning sheet, those worlds ended up orbiting in the same direction and the same plane. The flatness of the whole system, a preserved fossil of the disk that made it. Then we drew the crucial distinction. While the orbits of the planets faithfully record the disk's rotation, the individual spins of the planets do not have to, because a planet's own rotation is a fragile thing, set by the sum of countless impacts and vulnerable to being overturned by a single giant collision, tilted by tides, or reshaped by internal change. And finally, we watched angular momentum flow through the finished system, never created and never destroyed, but constantly redistributed, breaking the moon into a locked stare, lengthening Earth's day while lifting the moon's orbit, sculpting the crisp edges of rings and drawing families of moons into their rhythmic, resonant dances. Step back and look at what this all rests on, and you'll see it's the same small handful of ideas from the very beginning. No new machinery required. A tiny asymmetry, the lumpiness and faint turn of the cloud. Gravity, pulling inward and driving the collapse. Conservation of angular momentum, converting a whisper of rotation into a genuine spin as the radius shrank, then insisting that spin be flattened into a disk and later shuffled from body to body rather than ever disappearing. That is the entire mechanism, and out of it comes something as intricate and organized as a solar system, with its coplanar orbits, its spinning worlds, its ringed giants and resonant moons. None of it needed a designer or a cosmic hand to set it turning. It needed only an imperfect cloud and the rules that govern falling, spinning matter. There's a thought I'd like you to carry forward as we go. Everything we've seen at the scale of a single star and its planets is, in a sense, a rehearsal for larger performances, and also an echo of smaller ones. The protoplanetary disk that built the planets has the same essential shape and origin as the ring around a giant planet, and as the disk of moons that forms around that giant, and as we'll soon see, as the great disks of gas that swirl around dying stars and even around black holes. The flattening of rotating collapse into a disk is one of nature's favorite moves, performed at scales from a planet's rings to an entire galaxy. Once you recognize it, you start seeing it everywhere. The same silhouette repeating across a billion-fold range of sizes. And the redistribution of angular momentum, the shuffling we watched in the disk and the tides and the rings, is going to grow into one of the central characters of our whole story. Because when we reach stars and their violent deaths, and then the collapsed remnants that spin hundreds of times a second, and finally the galaxies themselves, the question again and again will be, where did the angular momentum go? How did this object get rid of enough spin to collapse, or gain enough to whirl so fast? And the answer, every time, will be some version of what we've already seen. It was handed off. To a disk, to a wind, to a tide, to a companion, to the surrounding sea of matter. Never gone. Always somewhere. So let's carry the seed onward and upward. We've watched it build a family of worlds around a single ordinary star. Now let's turn to the stars themselves and ask why they spin at all, why some barely turn while others whirl, and what happens to all that rotation when a star reaches the end of its life and its core comes crashing down into something far smaller, far denser, and far, far faster than anything we've met so far. Let's turn now to the stars themselves. We watched a cloud collapse and spin up and flatten into a disk, with a young star blazing at its center. But we rushed past that star to get to its planets. Now let's slow down and ask about the star directly. Does it spin? And if it does, where did that spin come from? And what happens to it over the star's long life and violent death? The answer to the first question is yes. Stars spin, and by now you can already guess why. A star forms from the dense central region of exactly the collapsing, rotating cloud we've been following. That central material fell inward along with everything else, shrinking enormously, and conservation of angular momentum spun it up right alongside the disk. So a newborn star inherits rotation for the same reason the disk does. It's made of infalling gas that carried a whisper of the cloud's turn, concentrated and amplified by the collapse. Our own sun rotates, completing roughly one turn every 25 days or so at its equator. That's leisurely compared to what we'll see later, but it's real, and it's a leftover of the spinning cloud that made it, just as the planet's orbits are. But here's a puzzle that troubled astronomers for a long time, and it leads us straight into one of the most important processes in a star's life. If a conservation of angular momentum spins up collapsing material so ferociously, and if a star is the most collapsed part of the whole cloud, having fallen inward the farthest, then a newborn star should be spinning outrageously fast. It should be whirling near the edge of flying apart. And yet stars like the sun turn slowly and calmly. Something must have stripped away most of the angular momentum the star should have inherited. Something must have carried it off. So where did it go? This is where our theme of redistribution becomes essential, because a young star has a remarkable way of getting rid of unwanted spin, and it involves the disk we already met and the star's own magnetism. The process is called magnetic braking, and it's worth understanding carefully because it's one of nature's great tricks for moving angular momentum around. A young star is threaded with magnetic fields, invisible lines of magnetic force reaching out from the star into the surrounding disk of gas. Now, the gas in a disk is hot enough to be electrically charged, and charged gas is gripped by magnetic fields. It can't slide freely across the field lines, but is instead forced to move along with them, as though beads were threaded on stiff wires. So the star's magnetic field lines act like a set of rigid spokes reaching outward from the spinning star into the disk. As the star turns, these magnetic spokes sweep around, and they grab the disk material and the gas above the star, forcing it to move. In effect, the fast-spinning star uses its magnetic field to take hold of the slower, more distant material and drag it along. but dragging the outer material costs the star something. By Newton's old rule that every push has a push back, the outer gas pushes back on the star through those same field lines, and that backward push is a brake. The star is slinging material outward along its magnetic spokes, and in doing so, it hands its angular momentum to that material and slows its own spin. There's a second piece to this, and it works hand in glove with the first. Young stars don't just sit there. They blow powerful stellar winds and shoot out jets of gas, streaming material away into space. That escaping material is also charged, and so it too is gripped by the star's magnetic field. As the wind flows outward, the magnetic field forces it to keep pace with the star's rotation out to a considerable distance, like water flung off the rim of a spinning sprinkler. By the time that material finally breaks free and sails off into space, it's carrying a disproportionate share of angular momentum away with it, far more than its small mass would suggest, precisely because the magnetic field kept it turning at the star's rate out to a large radius. Remember the leverage of distance. A little mass carried far from the axis while still turning fast hauls away a lot of angular momentum. So the star, over millions of years, spins itself down by throwing angular momentum outward, some into the disk through its magnetic spokes, and some into the fleeing wind and jets. Notice once again, the conservation law is never violated. The star didn't destroy its excess spin. It transferred it into the disk, into the wind, into the jets, into the surrounding sea of gas that eventually merges back into the galaxy. This is exactly the redistribution we watched in the protoplanetary disk and in the tides, now operating to tame a young star's rotation. It's the same lesson yet again. Angular momentum moves, it does not vanish, and this is the resolution of the puzzle. Stars like the Sun spin slowly, not because they never had much angular momentum, but because they had a mechanism to give most of it away in their youth. A slowly turning star is a star that successfully braked itself. Now, a star's rotation is not fixed for life. It changes as the star itself changes, and the reason is always the same principle: change the size of a rotating body, or move its mass around, or let it shed material, and its spin responds. Over its main life, a star like the Sun stays roughly the same size and rotates at a roughly steady, slow pace, having already done most of its braking. But when a star nears the end of its life, dramatic changes in size come, and rotation changes right along with them. Consider what happens to a Sun-like star as it ages. When it exhausts the hydrogen fuel in its core, the star swells enormously, ballooning outward into a red giant, growing to many times its original size. And here, conservation of angular momentum runs in reverse of the collapse story. The skater, remember, sped up by pulling her arms in. A star swelling into a giant is doing the opposite. It's throwing its arms out, expanding its outer layers to a vast radius. And so, for that expanding material, the rotation slows. The bloated outer envelope of a red giant turns sluggishly, its spin diluted across a much larger size. This is one reason giant stars can rotate very slowly at their surfaces. They've expanded, and expansion, by the same conservation law, drains the apparent spin. As an example, a red supergiant like Betelgeuse, swollen to a size that would swallow the inner planets if it set where our Sun does, turns extraordinarily slowly at its distended surface, its rotation spread thin across that enormous girth. But, and this is the crucial thing, while the outer envelope of such a star puffs out and slows, something very different is happening deep inside. The core of the star, no longer supported as it once was, begins to contract. And a contracting core does what contracting things always do. It spins up. So an aging star can develop a striking split personality, a vast slow-turning outer envelope wrapped around a small, fast-spinning core. The star as a whole looks like it's barely rotating, judging by its bloated surface, while hidden at its heart, a dense core is winding up tighter and tighter. Keep that image firmly in mind, because it's the direct setup for the most extreme rotation in the entire universe. The slow giant and its fast core are two halves of the same conservation law, one expanding, one contracting, pulling the spin in opposite directions. Now let's follow that contracting core to its conclusion, because when a star dies, the core's fate is where our story reaches its most spectacular heights. What happens to the core depends on how massive the star was, and it leads to 3 different kinds of collapsed remnant, each spinning far faster than the star that made it. For a star like the Sun, the ending is relatively gentle. The outer layers drift away into space, and the core is left behind as a white dwarf, an object with roughly the mass of the Sun packed into a ball about the size of the Earth. Think about that compression. The core, which was already contracting and spinning up inside the dying star, is now exposed as a body squeezed down to planetary size. All the angular momentum that core held is now concentrated in that small, dense sphere, and by conservation, its rotation is correspondingly quicker than the original stars. A white dwarf can complete a turn in hours rather than the days a star like the Sun takes, and some spin faster still. It's the skater's arms pulled in hard, the core's leftover rotation crushed into an Earth-sized package and sped up accordingly. But this raises an obvious question. If gravity is crushing the core down so ferociously, and if the core has no more nuclear fuel burning to push back with heat and pressure, what stops it from collapsing further? Why does it settle at the size of the Earth rather than continuing to shrink forever? The answer is one of the strangest and most important facts in physics, and it will matter enormously in a moment. The white dwarf is held up by something called electron degeneracy pressure. Here is the essence of it, without the mathematics. In the crushed interior of a white dwarf, matter is squeezed so tightly that the electrons, the tiny particles that normally drift around the outsides of atoms, are packed shoulder to shoulder. And there is a deep rule in quantum physics that says 2 of these particles simply cannot be forced into the exact same state, cannot be squeezed into the same place, moving the same way. They resist. Push them closer and they push back, not because of heat, not because of any fuel burning, but purely because the rules of quantum mechanics forbid them from being crowded any further. This resistance is a pressure, and it's a stubborn one. It's what holds the white dwarf up against its own gravity, freezing the collapse at roughly Earth size. So the white dwarf sits there, a dead ember with no fuel left, kept from further collapse by nothing but the refusal of its electrons to be packed any tighter. It will simply cool and fade over billions of years, spinning steadily, going nowhere. Remember that this support has a limit though. Hold on to that because it decides what happens to heavier stars. For heavier stars, the ending is far more violent and the compression far more extreme. When a massive star dies, its core is heavier than a white dwarf's stubborn electrons can hold up. That electron degeneracy pressure we just met has a ceiling, a maximum weight it can support, and beyond that ceiling it simply fails. The gravity wins. The core collapses catastrophically in a fraction of a second, And as it does, the electrons are crushed into the atomic nuclei themselves. Matter is compacted almost beyond belief, and the outer layers of the star are blasted away in a supernova, one of the brightest explosions in the universe. What's left at the center, if the collapse doesn't go all the way to a black hole, is a neutron star. And a neutron star is where conservation of angular momentum shows its most breathtaking face. A neutron star takes the mass of a star, more than the sun's, and crushes it down into a sphere only about a dozen miles across, roughly the size of a city. This is a collapse of unimaginable proportions. From a stellar core hundreds of thousands of miles across, down to something you could drive across in 20 minutes. And we know exactly what such a colossal collapse does to rotation. The leverage is staggering. That factor where rotation climbs with the square of how much the radius shrinks, the same rule that spun up the molecular cloud, is now applied to a collapse of a factor of tens of thousands. The result is that a neutron star can spin not once a day, not once an hour, but many times every single second. Some neutron stars turn dozens of times per second. The fastest turn hundreds of times per second. Their surfaces moving at a good fraction of the speed of light, whirling so fast, it's a genuine wonder they hold together at all. Let me put this in the language we've been building. A neutron star spins ferociously fast for precisely the reason the skater speeds up, and the whirlpool tightens, and the protoplanetary disk winds up. It inherited the angular momentum of its parent star's core, and then it collapsed to a tiny fraction of its former size, and conservation of angular momentum did the rest. The star didn't need to be spinning outrageously beforehand. A core turning at a modest rate, crushed down by a factor of tens of thousands, comes out the other side spinning hundreds of times a second. This is the ultimate demonstration of the principle we followed all night. Contraction reveals and amplifies rotation, and the more extreme the contraction, the more extreme the spin. Many of these rapidly spinning neutron stars announce themselves to us in a remarkable way as pulsars. A neutron star typically has an intense magnetic field, and that field channels beams of radiation out from its magnetic poles like a pair of searchlights. If the magnetic poles don't line up with the rotation axis, then as the neutron star spins, those beams sweep around and around, sweeping through space like the beam of a lighthouse. And if the Earth happens to lie in the path of one of those sweeping beams, we detect a pulse of radiation each time the beam points our way. Flash, 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 with astonishing regularity. That regular flashing is the neutron star's rotation made visible. When we time the pulses, we're literally clocking the spin of a collapsed stellar core, and the fastest of them are flashing hundreds of times a second. A direct readout of a rotation rate that beggars belief. Now, I need to be careful here, because it would be easy to overstate this and imply that all neutron stars spin at the same tremendous rate. They don't. Neutron stars are born spinning fast, but they come in a wide range of rotation rates, and those rates change over time. In fact, an ordinary young neutron star gradually slows down over thousands and millions of years. And once again, the reason is redistribution, the transfer of angular momentum away from the object. That intense magnetic field, sweeping through the surrounding space and driving radiation and particles outward, acts as a brake, much like the magnetic braking of a young star, but far stronger. The neutron star flings energy and particles away along its magnetic field. And in doing so, it hands off angular momentum and slowly spins down. So a neutron star's blistering birth rate is not permanent. It bleeds rotation into its surroundings over cosmic time, and the pulses gradually slow. Conservation isn't broken. The angular momentum is being carried off into space. Different neutron stars of different ages and histories therefore spin at very different rates, from hundreds of times a second down to once every several seconds. But there's a twist that ties directly back to our theme, and it produces some of the fastest spinning objects known, the millisecond pulsars. You'd expect the very oldest neutron stars to be the slowest, having spun down for 1 billion years. And yet we find ancient neutron stars spinning astonishingly fast, hundreds of times a second, faster even than many young ones. How can an old, spun down neutron star be whirling so quickly? The answer is that it got spun back up, and the mechanism is beautiful, because it's the disk story all over again. To understand it, we need to picture where these neutron stars live, because many of them are not alone. Stars very often come in pairs, 2 stars born together from the same cloud and bound in orbit around each other for their whole lives. When one member of such a pair is the massive star that dies and leaves a neutron star behind, the result is a neutron star locked in orbit with a still living companion star. For a long time, the two can coexist quietly, the dead remnant circling its living partner. But then the companion begins to age, and as we've seen, an aging star swells into a giant. And here is the crucial thing. As the companion swells, its outer layers can bloat so far that they reach the point where the neutron star's fierce gravity is stronger than the companion's own grip on its surface. At that boundary, gas begins to peel away from the companion and stream across the gap toward the neutron star, a bridge of glowing material flowing from the living star to the dead one. That streaming gas, falling toward the neutron star, cannot fall straight in, for exactly the reason gas couldn't fall straight into a young star. It has angular momentum, so it settles into a rotating disk swirling around the neutron star, an accretion disk. And this is where these systems reveal themselves to us. The gas spiraling through that disk is compressed and heated to such ferocious temperatures that it glows not in ordinary light, but in X-rays, the high-energy radiation we detect pouring out of these pairs. We call them X-ray binaries, and when astronomers find a bright, flickering source of X-rays in the sky, they are very often looking at exactly this: a dead neutron star feeding on the swollen body of its companion, the stolen gas blazing as it spirals down. Then, spiraling inward through that disk, the gas finally lands on the neutron star's surface, and as it does, it delivers its angular momentum to the neutron star, giving it a push, spinning it up. Grain by grain, over long ages, the infalling matter winds the neutron star tighter and tighter, until an old, slow, dead-seeming remnant is whirling hundreds of times a second once more, reborn as a millisecond pulsar. The angular momentum to do this came from the orbiting gas, stripped off the companion, transferred through the accretion disk onto the neutron star. Redistribution, one final time, spin handed from a companion star's material through a disk onto a collapsed core, spinning it back up. The same shape, the same principle, the same conservation law we started with, now resurrecting a dead star's rotation. So we've seen how contraction can wind rotation up to hundreds of turns a second, and how transfer can both slow a spinning remnant down and later spin it back up. Which brings us to the most extreme objects of all, the black holes and to a set of ideas that require us to think a little differently, because a black hole is not a solid object at all. Black holes can spin. In fact, most black holes that form in nature are expected to be spinning, and often spinning very fast, for reasons that should now feel familiar. A black hole forms from the collapse of a massive stellar core, the same kind of core that we've watched contracting and winding up inside a dying star. If that core carried angular momentum, and it did, then the black hole it forms inherits that angular momentum, because the conservation law applies to black holes just as it applies to everything else. The angular momentum can't simply vanish when the core collapses past the point of forming a neutron star. It has to go somewhere, and much of it goes into the black hole itself. So black holes are born spinning, carrying the rotation of the core that made them. But here we have to be careful with our picture, and this is genuinely important. A spinning black hole is not a solid ball turning on an axis, like a spinning planet or a spinning top. A black hole isn't made of ordinary matter with a surface you could paint a dot on and watch go around. A black hole is a region of space where gravity has become so overwhelming that nothing, not even light, can escape from within a certain boundary called the event horizon. When we say a black hole spins, we don't mean a solid object is rotating through space. We mean something subtler and stranger. The angular momentum of the black hole is expressed in the very geometry of the space and time around it. The rotation is a property of the warped space-time itself, not of a physical spinning surface. This is one of those places where our everyday intuition, built from spinning tops and turning wheels, simply has to be set aside, and we describe the rotation through the shape of space-time rather than the motion of solid stuff. And a spinning black hole does something to the space around it that has no everyday parallel at all, an effect called frame dragging. Let me try to give you a feel for it. Imagine space itself as a thick, honey-like fluid, and imagine the spinning black hole as a rotating ball immersed in that honey. As the ball turns, it drags the honey around with it, so that the honey near the ball is swept along in the direction of the spin. Now, space isn't really honey, but a spinning black hole really does drag the space and time around it into rotation. Near a spinning black hole, space itself is being swept around in the direction the black hole turns, and anything in that region, any bit of gas, any beam of light, any hapless object, is carried along by the rotating space, forced to circulate whether it wants to or not. You literally cannot sit still next to a spinning black hole, because the space you'd be sitting in is itself being whirled around. That's frame dragging, the rotation of the black hole reaching out and twisting the very fabric of space and time in its vicinity, setting it turning. It's the angular momentum of the black hole made manifest not as a spinning surface, but as a whirlpool in space-time itself. This frame dragging leads to something genuinely bizarre, a region around a spinning black hole with no counterpart anywhere else in nature. Close to the black hole, but still outside the point of no return, there is a zone where the dragging of space becomes so overwhelming that it is no longer merely difficult to sit still, it's flatly impossible. In this region, space is being swept around so fast that nothing whatsoever can resist being carried along with the rotation. You could fire the most powerful engine imaginable in the opposite direction, and it would make no difference. You would still be dragged around the black hole in the direction of its spin, because the space you occupy is itself circulating faster than anything can travel through it the other way. This region is called the ergosphere, and here's the remarkable part. It lies outside the event horizon, which means you could in principle venture into it and still escape, still climb back out, unlike the horizon itself where escape is forever impossible. Within the ergosphere, you are forced to orbit, compelled to turn with the black hole, and yet you are not yet trapped. It is a zone where the black hole's rotation has seized control of space without quite closing the door. Nothing about a still, non-rotating black hole produces such a place. The ergosphere exists purely because the black hole spins a whole region of the universe conscripted into the black hole's rotation. There is also a ceiling on how fast a black hole can spin, which is worth knowing because it echoes the white dwarf's limit in a curious way. A black hole cannot rotate arbitrarily fast. There is a maximum spin rate it can have for its mass, and if you tried to push it past that maximum, the very structure that makes it a black hole would break down. As matter and angular momentum fall in, a black hole can be spun up closer and closer to this limit, but never beyond it. So even here, in the most extreme object we know, rotation is not unbounded. There is a fastest a black hole is allowed to turn, just as there was a heaviest a white dwarf's electrons could support. The universe permits ferocious spin, but it does not permit infinite spin. And around black holes, as around neutron stars and young stars before them, matter that comes close forms a rotating accretion disk, for the very same reason it always does. Gas drawn toward a black hole carries angular momentum, and angular momentum, as we have seen again and again, will not permit a straight plunge to the center. The gas must settle into a swirling disk, orbiting the black hole while slowly spiraling inward, as friction lets it shed angular momentum to material farther out. These accretion disks around black holes are among the most luminous objects in the universe, because the infalling gas is compressed and heated to ferocious temperatures as it spirals down, blazing with radiation before it finally crosses the event horizon and disappears. When you see an image of a black hole ringed by a glowing disk of material, you are seeing the same physics that built the planets, the same physics that spun up the millisecond pulsar, rotating matter that cannot fall straight in, flattening into a disk and shedding its angular momentum outward so that a little of it can finally fall to the center. Disks around a newborn star, disks around a dying star's remnant, disks around a black hole, all the same silhouette, all the same principle, spanning an almost inconceivable range of scales. Let me draw this long stretch of the journey together because we've climbed from ordinary stars all the way to the most extreme objects in existence. And it's all been one continuous idea. Stars spin because they form from collapsing, rotating clouds, inheriting the whisper of the cloud's turn. Young stars spin more slowly than they otherwise would, because magnetic braking lets them fling angular momentum into their disks and winds, transferring it away rather than destroying it. As a star ages, its rotation changes with its size. Swelling into a giant slows the bloated outer envelope, while the contracting core hidden inside winds up faster and faster. The two halves of one conservation law pulling in opposite directions. When the star dies, that fast-spinning core is exposed and compressed into a remnant. And the more extreme the compression, the more extreme the spin. A white dwarf turning in hours, held up against gravity by the stubborn refusal of its electrons to be crowded further. a neutron star turning many times a second, its ferocious rotation the direct product of a collapse by a factor of tens of thousands. Neutron stars slow over time as their magnetic fields carry angular momentum away, yet they can be spun back up to hundreds of turns a second by accreting matter from a companion through a disk, reborn as millisecond pulsars in the glowing X-ray binaries where they feed. And black holes, born spinning from collapsing cores, express their rotation not as a turning solid, but as a whirlpool in the geometry of space-time, dragging space itself around them, opening an ergosphere where nothing can stay still, and gathering in falling matter into blazing accretion disks. Not one of these steps required a new principle. Every single one is the seed from the very beginning, planted in ever more extreme soil. A tiny asymmetry gives a cloud its faint turn. Gravity drives the collapse. Conservation of angular momentum spins things up as they shrink and slows them as they swell. And above all, insists that rotation be transferred, never destroyed. Whether it's flung out on magnetic field lines, carried off by a stellar wind, radiated away by a pulsar, or delivered inward by an accretion disk. The whole ferocious zoo of spinning stellar remnants, from the stately white dwarf to the blistering millisecond pulsar to the space-time whirlpool of a black hole, is that one modest idea, followed faithfully down to its most spectacular conclusions. Hold on to the two motifs that have carried us this far, because they're about to be tested at the grandest scale of all. The first is contraction and amplification. Shrink a rotating thing, and its spin roars up, more violently the more it shrinks. The second is transfer, not destruction. Angular momentum flows from body to body into disks and winds and radiation and orbits, but the total is always preserved. We've watched both play out across a planetary system and across the life and death of stars. Now we have to ask whether they still hold when we zoom out to the largest rotating structures in the cosmos, the galaxies, with their hundreds of billions of stars turning together in the dark. And we'll find, as we might expect, that a galaxy does not turn the way any of the things we've seen so far turn. And that understanding the difference reveals something profound about what a galaxy really is. Now let's zoom all the way out to the largest rotating things in existence, the galaxies. A galaxy like our own Milky Way is a vast wheel of a few 100 billion stars, turning slowly in the dark. Our sun is one of those stars, carried around the galactic center once every couple of 100 million years or so. And it would be natural to picture the galaxy turning the way everything we've met so far turns, like a spinning record or a great cosmic wheel, rigid, all of one piece, the whole thing rotating together. But this picture is wrong. And understanding why it's wrong is the key to understanding what a galaxy actually is. Here's the problem with the spinning wheel picture. On a solid wheel, every part completes one turn in the same amount of time. A point near the rim and a point near the hub both come back around together because they're locked into the same rigid body. The rim simply has to travel faster to keep up, since it has farther to go. If a galaxy turned like that, the outer stars would race around at tremendous speed to stay in step with the inner stars, all completing their circuits in unison. But a galaxy is nothing like a solid wheel. It has no rigid structure holding its stars in fixed positions. It's a loose swarm of hundreds of billions of separate stars, each one an independent object, each one simply following its own path under the pull of gravity. Nothing connects one star to its neighbors, the the way the material of a wheel connects rim to hub. Each star is on its own, so a galaxy does not rotate as one rigid object. Instead, each star traces its own orbit around the galactic center, at its own speed, set by the gravity it feels at its particular distance. A galaxy's rotation is really the sum of countless individual orbits, hundreds of billions of stars each revolving around the shared center in its own good time. This is much closer to the orbital motion we discussed at the very beginning, planets going around the sun, than to a single object spinning on its axis. A star near the center and a star far out are not locked together. They orbit independently, and they generally take different amounts of time to complete a lap. The galaxy has an overall sense of rotation, a direction most of its stars share, but it turns the way a swarm turns, not the way a wheel turns. Stars drift past one another, inner ones lapping outer ones over cosmic time, the whole pattern shearing and winding rather than rotating rigidly. When you see a beautiful image of a spiral galaxy and it looks like a solid pinwheel, frozen in the act of turning, remember that it's an illusion of the snapshot. Those arms are not rigid spokes. They're patterns in a swarm of independently orbiting stars, and the swarm is not turning altogether. Now, this way of rotating as a swarm of independent orbits immediately hands us one of the great mysteries of modern astronomy, and it connects our whole story of rotation to something invisible. When astronomers carefully measured how fast stars orbit at different distances from a galaxy's center, they expected the outer stars to orbit more slowly than the inner ones. That's what happens in the solar system. The planets close to the sun orbit quickly, and the distant planets orbit slowly, because the sun's gravity weakens with distance. So out at the edge, there's less pull, and the orbits are lazier. A galaxy's visible matter, its stars and glowing gas, is concentrated toward the middle. So out in the sparse outskirts, you'd expect the pull to weaken and the orbits to slow, just as they do for the outer planets. But that's not what the galaxies show. When astronomers measured the orbital speeds of stars and gas far out in the thin outer regions of galaxies, they found those distant stars orbiting just as fast as stars much closer in. The outskirts weren't slowing down the way the visible matter said they should. The stars way out at the edge were racing around far too quickly to be held by the gravity of the visible material alone. By rights, moving that fast, they should have been flung off into intergalactic space long ago. Something was holding them in, something with a great deal of gravity that we could not see. That something is what we call dark matter. The rotation of galaxies is one of the main reasons we believe it exists. To keep those fast-orbiting outer stars gravitationally bound, a galaxy must contain far more mass than its stars and gas account for, and that extra mass must extend well beyond the visible edge, out into a vast surrounding halo. It doesn't glow, it doesn't block light, it seems to interact with ordinary matter almost entirely through gravity, which is why we can't see it directly. But its gravity is what governs how the outer parts of galaxies rotate. In a real sense, the way a galaxy turns is dictated less by the stars we can see than by the invisible halo we can't. I won't go further down this road tonight, because dark matter is a vast subject of its own, but the essential point for us is this. A galaxy's rotation is shaped by a shared gravitational field that most of its stars orbit within, and that field is dominated by unseen mass. The stars are not embedded in a rigid spinning disk. They're orbiting through a shared gravitational potential, most of which is invisible. But this raises the same question we've asked at every scale. Where did a galaxy's rotation come from in the first place? A galaxy holds an enormous amount of angular momentum, all those hundreds of billions of stars orbiting the same way. By the rule we've followed all night, that angular momentum could not have appeared from nothing. It had to be inherited, generated by some imbalance and interaction early on. So how did galaxies get their spin? The answer takes us back to the earliest structure in the universe, and to a lovely mechanism called tidal-torque. In the early universe, matter was drawing itself together into clumps that would become galaxies, but these forming clumps were not isolated. Each one had neighbors, other growing clumps nearby, and each one was irregular, lumpy, never a perfect sphere. And here's the key. A lumpy, irregular clump sitting in the gravitational field of its neighbors feels an uneven pull. One part of the clump gets tugged a little harder than another part because it's a little closer to a neighbor or a little denser. That uneven pull is a twist, a torque. Just as you spin a wheel by pushing harder on one side than the other, the neighboring clumps of matter twisted the forming galaxies by pulling unevenly on their irregular shapes. Every proto-galaxy was gently torqued by the gravity of everything around it, and that torque set it slowly turning. This is tidal torque, the twisting of a forming galaxy by the uneven gravity of its surroundings, in the era before galaxies had fully separated from one another. It's the same family of physics as the tides that raise bulges on the Earth, now operating on the scale of embryonic galaxies and setting them spinning. Notice how this fits everything we've built. The angular momentum of a galaxy did not come from nowhere. It came from asymmetry, the lumpiness of the forming clump, and from interaction, the gravitational tug of neighbors. Those are two of our three original ingredients. Imbalance and gravitational interaction now producing spin at the largest scale of structure. And once a proto-galaxy has been given that initial twist, the rest of the story is familiar. The clump collapses, and as it collapses and shrinks, conservation of angular momentum spins it up, and rotation that was gentle at the enormous scale of the early clump becomes the organized rotation of a galaxy. Tidal torque plants the seed of spin. Gravitational collapse amplifies it. The same two-step we've seen at every scale. Galaxies also gain and change their angular momentum in other ways, and the most dramatic is through mergers. Galaxies are not fixed and final. They grow over cosmic time by colliding and merging with other galaxies, and each merger dumps a great deal of angular momentum into the mix, or cancels some out depending on how the galaxies come together. When two galaxies fall into each other, and their orbits carry them around one another before they combine, all that orbital angular momentum of the collision gets folded into the rotation of the merged galaxy. Galaxies also grow more gently, by accretion, drawing in streams of gas and small companion galaxies from their surroundings. And each of these arrivals carries its own angular momentum, adding to or subtracting from the galaxy's spin. So a galaxy's rotation is not a single inheritance frozen at birth. It's the running total of everything the galaxy has torqued, collapsed, merged with, and swallowed over billions of years. All of it bookkept by the conservation law, none of it created from nothing. And mergers show us the destructive side of this too, which matters, because we should never imagine that rotation, once established, is somehow guaranteed to be neat and permanent. When two galaxies collide head-on, or when a merger brings their angular momenta into opposition, The organized rotation of the original galaxies can be scrambled, reduced, or largely erased. The orderly disk of a spiral galaxy, all its stars circling the same way, can be torn apart in a major collision, its stars flung onto a jumble of orbits pointing in every direction. The result is often an elliptical galaxy, a great swarm of stars orbiting this way and that with a little overall rotation, its former organized spin cancelled out and randomized by the violence of the merger. So rotation can be built up by torque and collapse and accretion, and it can be broken down and disordered by collision. It's not a one-way street. The angular momentum is still conserved through it all, of course. In a collision, it's redistributed and redirected, some of it cancelling as opposing spins meet, some carried off by stars flung out into space, but the tidy, organized rotation of a disk is a fragile achievement that a merger can undo. Now I want to head off a tempting mistake, because we've been climbing to larger and larger rotating structures, and you might expect the pattern to just keep going. If stars orbit in galaxies, and galaxies rotate, then surely galaxies orbit in rotating clusters, and clusters in rotating superclusters, all the way up. But this is where the ladder of rotation runs out, and it's important to be honest about it. Galaxy clusters, the great collections of hundreds or thousands of galaxies bound together by gravity, do not rotate coherently as single spinning objects. The galaxies within a cluster do move, swarming around inside the cluster's shared gravitational field on all sorts of orbits. But the cluster as a whole is not a great wheel turning about an axis. Its galaxies buzz around like a swarm of bees in every direction without the organized net rotation that a single galaxy has. And on the largest scales of all, the cosmic web, that vast network of filaments and sheets and voids along which galaxies are strung, matter is flowing, draining out of the empty voids and streaming along the filaments toward the dense knots where clusters gather. But these large-scale cosmic flows are not a coherent rotation either. They're more like slow currents of matter falling under gravity toward the densest regions, not a spinning of the whole structure about some center. Why does organized rotation fade out at the largest scales? It comes back to what we said at the very beginning. Rotation gets built up and amplified when matter collapses, when a structure contracts by a large factor, because that's when conservation of angular momentum spins things up so powerfully. A star, a planetary system, a galaxy, these are all things that have collapsed enormously from a much larger initial cloud, and that collapse is what wound up their rotation. But galaxy clusters in the cosmic web have not collapsed by anything like the same factor. They are still spread out, still loosely assembled, still in many cases in the process of gathering. Without that dramatic contraction, there's no powerful spin-up, and so the larger structures never acquire the organized rotation that collapsed objects have. This is a crucial point in our whole story. Rotation is common precisely at the scales where things have collapsed, and it fades where they haven't. It's not that the universe rotates at every scale, it's that rotation emerges wherever gravity has driven a real collapse, and it's absent or feeble where collapse hasn't happened, which brings us naturally to the biggest question of all. Does the universe as a whole rotate? We've found rotation almost everywhere we've looked, from planets to stars to galaxies, so it's tempting to imagine the entire universe turning about some grand cosmic axis, one final, ultimate rotation containing all the others. But here we have to be very careful and very honest, because the evidence points the other way. There is no established evidence that the universe as a whole is rotating around any cosmic axis. Local rotation is everywhere, yes, Planets spinning, stars spinning, galaxies turning, but that's local rotation, each object turning about its own center, with the axis pointing in all different directions. No two galaxies obliged to spin the same way. When we add it all up across the whole cosmos, these countless local rotations point every which way and largely average out. They do not seem to combine into one grand rotation of everything about a single axis. And we can actually test this, which is remarkable. If the universe as a whole were rotating, it would leave subtle fingerprints on the largest observable things, especially on that oldest light, the afterglow of the early universe we spoke about at the very start. A rotating universe would tend to stir that ancient light in particular patterns, imprinting a kind of swirl or a preferred direction across the whole sky. Astronomers have looked carefully, and they don't find such patterns. The oldest light looks the same in all directions to extraordinary precision, with no sign of a global swirl. These observations place very strong limits on any possible rotation of the universe as a whole. They don't prove the rotation is exactly zero, because you can never measure anything as exactly zero, but they show that if the universe rotates at all, it does so unimaginably slowly, far too slowly to matter, so slowly that it would take vastly longer than the current age of the universe to turn even a tiny fraction of a full circle. For all practical purposes, and by all the evidence we have, the universe as a whole is not spinning. It has no confirmed cosmic axis. The rotation we see is local, filling the universe, but not the rotation of the universe. This is worth sitting with, because it fits our whole explanation perfectly. Rotation arises from the collapse of structures under gravity, from imbalance and interaction amplified by contraction. But the universe as a whole is not collapsing. On the larger scales, it's expanding, and expansion, as we saw with the red giant swelling and slowing, is the opposite of the contraction that winds up spin. So the universe as a whole has no mechanism to acquire a grand rotation, and indeed it doesn't appear to have one. Rotation is a feature of the things within the universe that have collapsed, not of the universe itself. I should add one more note of honesty here, because our title speaks broadly of everything spinning, and I don't want to leave you with an overstatement. It is not true that literally every object in the universe spins, nor that everything spins in the same way. Some objects may rotate extremely slowly, and some may have almost no net angular momentum at all, because their little bits of leftover motion happen to nearly cancel out, or because they transferred their spin away over time. There's no law that every single body must be turning. The honest claim is not that everything spins, but that rotation is extraordinarily common, that it emerges again and again wherever gravity collapses imperfect matter, and that when it emerges, the conservation law makes it hard to get rid of. Common is not the same as universal, and it's the commonness, not a false universality, that we've been explaining all night. There's also one kind of spin I've been carefully keeping separate from all of this, and now is the moment to draw the line clearly, because the word is the same, but the thing is entirely different. That's quantum spin. When physicists say that an electron or a proton or a photon has spin, they are not saying that a tiny ball of matter is rotating like a miniature planet. Quantum spin is an intrinsic property of a fundamental particle, a fixed amount of angular momentum the particle simply has, built into what it is, the way it has a certain mass or a certain electric charge. An electron's spin isn't the electron whirling around. The electron isn't a little sphere with a surface that goes around. And if you tried to picture it that way, the numbers wouldn't even make sense. The surface would have to move impossibly fast. Quantum spin is a genuinely quantum property with no true everyday counterpart. An inherent quantity carried by the particle, not a motion of stuff through space. It's called spin because it behaves mathematically like angular momentum, and adds up with the ordinary kind, but you should not picture it as a tiny particle physically spinning. It's a different thing wearing the same name. I mention it only to keep our accounting honest, and to make sure you don't walk away imagining that the spin of a galaxy and the spin of an electron are the same phenomenon at different sizes. They are not. Everything else we've discussed tonight, the planets, the stars, the neutron stars, the galaxies, is ordinary rotation, real matter moving around a center. Quantum spin stands apart, and having named it and set it aside, we'll leave it there. So let me gather the whole night together, because we've traveled from the smoothest possible beginning to the largest possible structures, and it has all, remarkably, been one single idea told over and over. We began with a universe astonishingly smooth and nearly motionless, and we asked how it filled itself with rotation. And we never once needed a mysterious universal spinning force. We needed only three things. First, imperfection. The early universe was smooth, but not perfectly smooth, and no real cloud, no forming galaxy, no collapsing core is ever perfectly symmetric. There are always tiny density variations, always faint sideways motions, always the uneven tug of neighbors, perfectly radial, perfectly symmetrical collapse, everything falling dead straight toward a center with no swirl at all, is a knife-edge condition as fragile as a needle balanced on its point, and the real universe, riddled with imperfection, essentially never achieves it. Those very imperfections are what carry the first whisper of angular momentum. Second, gravity. Gravity relentlessly pulls matter together, driving the collapse of clouds into stars and planets, of cores into neutron stars and black holes, of early clumps into galaxies. Gravity is the engine that takes those spread out, slowly drifting, faintly turning structures and makes them contract. And third, conservation of angular momentum. This is the rule that turns a whisper into a roar. As a rotating thing contracts, its spin must increase, and with a leverage so powerful that a barely detectable initial turn becomes a furious rotation by the time collapse is done. This is why the skater speeds up, why the whirlpool tightens, why the protoplanetary disk winds up, why the neutron star whirls hundreds of times a second. And this same law insists, just as strictly, that angular momentum is never destroyed, only moved, handed from inner disk to outer disk so a star can feed, flung out on magnetic field lines and stellar winds so a young star can slow, carried off by a pulsar's radiation, delivered inward by an accretion disk to spin a dead star back to life, folded into a merged galaxy or scrambled and cancelled in a collision, transferred from Earth's spin into the moon's slowly climbing orbit. Everywhere, always, the total is preserved even as it flows from place to place. That is the mechanism, whole and complete, and it explains both why rotation is so common and why it takes such wildly different forms at different scales. It's common because its absence would require a perfection the universe does not possess. Exact symmetry is rare. Perfectly straight in collapse essentially never happens, and once even a sliver of spin exists, contraction amplifies it, and conservation refuses to let it simply disappear. And it takes different forms because the objects have collapsed by different amounts, and transferred their angular momentum in different ways. A planet turning once a day, a star once a month, a white dwarf in hours, a neutron star hundreds of times a second, a galaxy as a swarm of independent orbits governed by invisible mass, and the largest structures of all barely rotating in any organized way at all, because they never truly collapsed. I'd like to leave you with the deepest version of what we found, the principle underneath the whole story. We asked why so much of the universe spins, and the truest answer turns the question inside out. The universe spins so widely, not because something said it's spinning, but because standing perfectly still is the hard part. Stillness, in a cosmos governed by gravity and shot through with imperfection, is the fragile, unnatural state, the balanced needle that any breath topples. The moment matter begins to gather and fall together, the faintest leftover motion is caught, concentrated, and revealed, and once revealed, it cannot simply be thrown away, only passed along. Rotation is common because exact symmetry is rare, because gravity amplifies every imbalance it finds, and because angular momentum, once it exists, must always be conserved or handed onward to something else. The turning planets, the spinning stars, the whirling remnants, the wheeling galaxies, all of them are the same quiet law made visible again and again across every scale where matter has fallen together in the dark. Not everything in the universe spins, but wherever the universe collapses something imperfect under its own gravity, spin is very nearly the only thing that can result, and that is why, whenever you look up, you are almost always looking at something turning,